This equation is the equation, quantum Schrodinger equation for a harmonic oscillator. But that has to stop somewhere. That is precisely the hallmark of a stable system. So this is your eigenspectrum for the simple harmonic oscillator. Hi guys, so welcome back to another video. I apologize I couldn't upload or make a video for maybe a week. I was not well, but yeah, hopefully I can right now. So briefly a recap. Let's recap what we did a week back. So in lecture 6 and 7 we basically met our first wave function. We solved this system where you were essentially a particle or a ball confined by an infinite potential on either side, right? Like we solved this problem so the potential that we solved for basically was the simplest one. The potential was 0. This is 0 if you were between x equal to 0 and a, and the potential rose to infinity otherwise. So this was the problem we solved in the last couple of lectures. So if you guys are joining me for the first time and if you guys want to brush up with it, you can look at the last couple of lectures. But let's begin. So today is lecture 8, and I want to solve probably the most important physics problem that you'd face in your career in physics. It is called the simple harmonic oscillator, or an SHO. So what's a simple harmonic oscillator? There are various ways of defining it, but imagine it's the motion of a spring coil. Classically, it's a motion of, so imagine this is a spring. So what happens when you pull a spring? So this is Hooke's law, right? Imagine this is the equilibrium point, and if you pull it a bit more, like by an amount delta x, then you know that the force you feel is proportional to minus kx or minus k delta x, right? So yeah, where k is a positive constant, or in other words, if you pull the string this way, the spring wants to recoil back. Likewise, if you push the spring this way, the spring again wants to go back to its original position, which is given here. So the motion of the spring is called a simple harmonic motion, and in classical mechanics you know what this motion is. So you simply solve Newton's second law, which tells you that m is proportional to the second derivative, and I told you that by Hooke's law this is equal to kx, right? So the equation of motion of the spring is given by this simple equation, which is x dot, where of course double dot means derivative with respect to time twice, x is equal to 0. You know this from classical mechanics, right? So tell me, what's the solution? X, which is x of t, will be given by a cos omega t plus b sine omega t, where omega is defined to be square root of k over m, right? Why is this a solution? Well, simply plug and plow, right? Simply take this equation, take the solution, take its double derivative, and you will see that this equation is satisfied. So this is the equation of motion of a spring, and this is also called a simple harmonic motion or a simple harmonic oscillator in classical mechanics. So now I want to solve the same problem in quantum mechanics. So same problem. In quantum mechanics. Well, in lecture 1, we studied the Schrodinger equation, right? And the Schrodinger equation, we needed to figure out the potential Vx. This was an input in the Schrodinger equation, right? Just as, for example, in this problem that we solved in lecture 6 and 7, I wrote that the potential was given is the simplest potential. It's simply 0 between 0 and a, and it's infinity otherwise. So you need to tell me, if you were to solve the Schrodinger equation, or in other words, if you were to tackle this problem using quantum mechanics, you need to tell me what this potential is. Well, this potential is very simple because I have told you what this force is. Force is proportional to delta x. So if your if if f equal to kx, then from high school physics we know that v is simply integral f dx, right? So it's half kx squared, right? Great. So problem 1, again, to just show that there is a continuity, the problem 1 in the last couple of lectures, lecture 6 and 7, Vx was constant equal to 0. This was problem 1. In problem 2 that we are trying to solve now is the next best thing, which is now you have a Vx which is given by half kx squared. And this is actually, as I mentioned, this is the first line attack, the first approximation that you would always do in physics. Why is that? Because recall, if you have, I think it's taught in high school these days, right? If you have any one dimension, a function of one variable, you can do a Taylor expansion. And what do you get about, say, x equal to some x naught, some point, any point in fact, you would get this series, right? Plus double derivative and so on and so forth. You know this series, right? This is called Taylor expansion for one variable x here. In physics, this term would always be 0. Why is that? Because forever in physics, you would be expanding, well, when you do quantum field theory later, you will see that you will be expanding whatever your whatever, it's called Lagrangian in that setting, but I don't want to confuse you. But the point being that whatever you would be expanding, you would be expanding near its minima. So you know, near its minima, this first derivative always vanishes near its extrema, right? For example, if I were to draw a random fx, you see these are called local extrema. Or in this case, minima. Generally they would be extrema, but here they are local minima. And you see, it's necessary that at these minimum points, the first derivative actually vanishes, right? In fact, you find out these minimas by solving by setting the first derivative to 0. So at these critical points, your first derivative is 0, right? So this is, say, an x star, is our x star, x star satisfies this equation. That's how one finds out these minimal critical points. Well, if your first derivative vanishes here, Your first order approximation is given by this term, right? So any fx would be given by half v, the double derivative, x minus x square, x minus x the whole square, plus higher order in x minus x0. This notation in physics or maths is called higher order. This is just saying that whatever correction terms you have, these are order x minus x naught cube and higher. That's what it means, okay? But you see, let's look at this equation. Let's look at this equation. You see, this is exactly of this form, right? Potential is, the first term is quadratic. And it is quadratic here. So this simple harmonic oscillator problem that you are going to learn about right now is the first correction that you will always get. Why correction? Because of course, this is a correction, right? You're trying to gauge what your fx is about this point x0. You're trying to gauge, for example, say the value of the function here near this point, near these critical points. So in that sense, this is a correction. This bit is the correction, right? This bit is the correction. This bit is fx minus f of x naught. So you see, the first order correction is always given by the harmonic oscillator. And this is true in every areas of physics. Even later when you do quantum field theory, this will be true. There, the first, in higher physics, this term will vanish using equations of motion. Equation of motion is exactly this equation. By definition, they are where your first derivative vanishes, or in other words, they extremize your action, so to speak. And the first correction, the quantum correction that you'd get, are basically quadratic in the differences, which is exactly this. So this is extremely crucial, a function that that would always be there in the as a first order correction to your problem. Okay, so that's some information that you'd probably need going forward. So let's try and now solve the Schrodinger equation. So, well, do you remember the Schrodinger equation, the time independent Schrodinger equation? This was done in lecture 1, right? So those of you who are joining me for the first time, so this Schrodinger equation we studied in the very first lecture, in lecture 1 itself. So this Schrodinger equation told you that to solve for the wave function, you need to solve this equation. Del 2 psi del x square plus vx psi x is equal to some e, we don't know what this e is, times, and have mentioned before that this is called an eigenvalue equation, right? This was also discussed, I think, in lecture 4 or 5. So they are all there in the playlist if you guys are joining later, or if you guys have forgotten what these are. Yeah, go through them. So this is the time independent Schrodinger equation, which we have discussed before. And now we figured out what this Vx is, right? We have figured out this Vx is half k x square, right? Which is the same as, say, half m omega square x square, right? So the equation that I want to solve is minus h square by 2m t2 psi dx square plus half m omega square x square psi of x, or psi of x is equal to some constant e that I need to figure out times psi of x. This equation is the equation, quantum Schrodinger equation for a harmonic oscillator. Okay, so how do I go about it? Actually, there are a couple of ways, but let me show you the simpler but a bit longer way first. I'll show you or discussed in the next lecture. There is an algebraic way of doing it, and it relates to group theory. I am sure most of my audience haven't worked out group theory. It comes a bit later in it doesn't appear in high school at all, and it comes later in undergrad physics. So the group theory method I'll do a bit later in the next class, in the next lecture actually. But let's do it in exactly the same way we solve for this problem. Okay, so let's try and figure out the spectrum by solving differential equations. That would be more comfortable initially. Okay, so let's try and solve for this. So what I need by solving for this, I need to figure out psi of x, and I need to figure out en. So this is what the goal is. So solve for these guys. So how do I go about it? Well, you see, this is a quadratic. This is second order in your derivatives, right? So maybe some of you are thinking, okay, why can't I factorize it, right? And that's, if you are thinking that, then you are already in the right track. The goal, or the smart way of solving it, is to try and factorize it. Okay, so in quantum in complex analysis, this holds, right? This from complex analysis. So you see, the reason I mention it is because this is a square, this is a square, so hopefully something along these lines would work out, right? Okay, let's try. So let me give you the answer first. So let's define these two operators. A plus minus is equal to 1 by root 2m h crossed by I del dx sorry, plus minus I m omega x. So the notation, it means if you take the upper row here, you have to take the upper sign here. If you take the lower sign here, you have to take the lower sign here. That's what this notation means, for those who don't know. Okay, I have randomly defined an operator. This is an operator. Why is it an operator? Because you see there is a derivative here. So this guy needs to act on a function. Otherwise, in itself, this doesn't make too much sense, right? So that's why it's an operator. These are called operators, specifically differential operators. Okay, so let's try and calculate, say for example, this guy. This is bit important, so please pay a bit of attention. The way of figuring this out is that since it's a differential operator, you always need, as I mentioned, it is imperative that it acts on some function. Otherwise, ddx itself doesn't make sense, right? Df dx makes sense. Ddx itself doesn't make too much sense. So the goal, the way of figuring out what this operator is to make it act on a function f of x. Well, just simply x, because you just have a differential operator which acts on x, right? Okay, so let's figure it out. So okay, let's start with following Griffiths. Let's start with a minus a plus first. So it's 1 by 2m. So as I mentioned, if you are to read the minus, you have to read the minus from here, right? The lower sign goes to the lower sign. So it's, oops, h cut by I t dx minus, because I'm taking the minus first. So this has to be minus, okay? This is clear, right? Minus I m omega x. Then I have the plus. So I need to take the plus now, right? So I'll write again h cut by I plus I m omega x. And I mentioned these two things together don't make sense unless it acts on an fx here. So this plus is this plus, and yeah, and since, oops, I missed the ddx. And since there is a derivative here, you definitely need a function. The derivative needs to act on something, okay? Otherwise, it doesn't make too much sense. Okay. So let's do it. This is equal to 1 by 2m h cross by I t dx minus I m omega x acting on this whole stuff, h cross by I tf dx plus I m omega x times fx, right? Okay. So let me do this. So this gives you 1 by 2m. I'm actually being painstakingly slow. I hope you realize that, because this, maybe some of you are doing it for the first time, so I want to explicitly do all the steps. That's the whole point. We study together, right? So that, you know, there is no confusion. This should give you, and careful. So now this ddx acts on both, right? That's the whole point. You see, this is again why you need the fx here. If you did not have the fx here, you would probably simply and wrongly have just written the ddx without, you would have probably simply written this ddx acting on this x without the fx, and that would have been wrong. So let me clarify it again. That's why you need this ddx to act on this whole thing. Otherwise your result would be wrong, okay? Otherwise it doesn't make sense. Okay, I'm not done. So there would be some other terms, minus h cross m omega x dx. For example, this comes from this guy acting on this guy. I beg your pardon. Plus the quadratic term, right? M omega x whole square fx. You're almost done. So this is simply 1 by 2m h by I, h cut by I whole square. Nope. ddx whole square. Plus mx whole square. But you are not done. You see, there is an extra piece lying around, which is h cut m omega times fx. Do you see this? For example, the crucial part is the ddx acting on fx here cancels the df dx here. That's the whole point. So this ddx acts on this term and acts on this term. This is called Leibniz rule. You know this, right? Leibniz rule. When this ddx acts on the fx, it cancels this term. That's why in this expression, you don't have a df dx. Precisely why. So you get this term. So now you see, now you can read off what this a minus a plus is. So a minus a plus acting on fx is this whole thing acting on fx, right? So your a minus a plus, a minus a plus. Now you can write that this is just this expression. So that's the correct way. So that's the correct way of figuring copy. That's the correct way of figuring out these operators, the product of these operators. Actually, this is homework. If you guys are following or trying to learn, please do this exactly as I did this. Read the above. Try and figure out what this is. And you will see that this is not exactly the same thing. You will see, in fact, this would be almost the same as this, except a crucial sign difference. Copy. I'm being lazy. But yeah, this would be there will be a crucial sign difference, or in other words, this would be minus. Okay, let me highlight it for you. This is plus, this is minus. Crucial sign difference. So you see, these operators do not commute. What does it mean? Well, two operators a and b, well, we have a plus and a minus. Commute means this is equal to 0. This is definition. But you see, this is not 0, right? You see, in fact, so your a so it's convention to write the minus first. So it's non-zero. If it is non-zero, do not commute. If it is 0, then it does commute. But you see, these operators, they do not commute. In fact, this is equal to h cut by omega. Where do you get it from? You get it from this term. This cancels, and there are h cut omega by 2 and an h cut omega by 2. That gives you a discount. This is a crucial relationship in quantum mechanics. A minus a plus is equal to h cut omega times identity. This is called canonical commutation relation in quantum mechanics. Okay, great. We are doing good progress, okay? So now that you have this form, let's take a look at where we were. So we wanted to actually, where did we start from? We wanted to factorize this operator, right? We have almost factorized it. Or in other words, if you look at that expression and this expression, you see that the Schrodinger equation had this term and this term. You just have an extra term proportional to identity hanging around, right? So you know what to do? Well, so the Schrodinger equation is actually now can be written in this manner. Let me write it for you. So the Schrodinger equation becomes a plus a minus plus half h cross omega, very simple looking stuff, psi is equal to e psi. Do you agree? Let's check if it makes sense. So you see a plus a minus, you have to get rid of this extra piece, right? There is a minus h cross omega by 2 sitting here. So a plus a minus plus half h cross omega psi is the Schrodinger equation that you want to solve. Okay, we are almost done. Now we need a next observation, that if this equation, so pay attention, okay? If this equation holds, then the same operator, a plus a minus, acting on say a plus psi, would give you e plus. This is a claim. As things stand, it's not obvious at all. Okay. Let's check that the claim is right. Well, how do I figure this out? So let's start from the LHS. The LHS is say a plus, a, then I'm left with a minus, a plus from here, plus half h cross omega psi. This is the left hand side, right? I've just pulled out an a plus from here, and this a plus is this a plus, and these are just numbers, right? So it doesn't matter, you can pull it out, but you have to be careful. You have to be careful about the ordering of these operators, because these are operators, but this is a number. This is 5, 7, 13, whatever. So 5 into 3 is 3 into 5, right? So the ordering there doesn't matter, but these are say numbers, matrices for example sometimes. So that ordering doesn't matter. Okay, so you understand this. But you see, you have already worked out that this guy from this relation, from this standard canonical commutation relation, let me write it here. Okay, let me do it for you actually. Let me be absolutely pedantic and do it for you. This we have seen is the canonical commutation relation. This means this is equal to h cross omega. This is definition, which means a plus a minus is equal to a minus a plus minus h cross omega, right? So, okay, why did I do that? I wanted the other way around. So from here, a minus a plus is a plus a minus plus h cross omega, right? Do you agree? So let's substitute this relation here. You'll get an a plus a minus plus three by 2 h cross omega psi. Okay. Okay, so this is a plus say a plus minus plus half h cross omega psi plus h cross omega psi, right? I have done nothing other than break this 3/2 into half and 1. Great. Aha! But you know this equation I already know, right? This equation is simply this equation, which means this is a plus excuse me, e plus h cross omega psi. Why? Because this is e psi, right? Okay, that's it. We are done. So this proves the claim, right? That this is h cross a plus psi. Again, why is that? Because you have to be careful here. These are numbers, okay? 5, 7, 20 something. So of course this easily goes through. There is no problem here. So this is equal to this. So I have proved this for you. Exercise. Exactly as I did here, using this commutation relation, prove the following: that in fact the other way around, a minus, if you had a minus a plus, minus half h cross omega a minus psi is equal to e minus h cross a minus psi. Okay, exactly. So you had a plus minus here, and you have a minus plus here. The minus plus has an eigenvalue e minus h cross omega. Okay, so this I have done for you in gory details. This is something that you should do as an exercise. And now you already know. You can see that so this was. So you see that if psi, the claim is if psi has an eigenvalue e, then a minus e psi has an eigenvalue e minus h cross omega. Say a minus square will have an eigenvalue e minus 2 h cross omega, and da da da. You have, say, if you applied n times, you will have it still is an eigenvalue, eigenvector, and the eigenvalue would be this guy, just as you had an e to the power minus h for this operator, right? For this operator, you had, if you act it once, you get a minus once. If you act it n times, likewise, you get a minus n times. Exactly the other side of the story also holds. In fact, the other side of the story is the one that we did before. Your a plus psi would be an eigenvalue with would be an eigenfunction with eigenvalue e plus h cross. Say if you have a square, it would have dot dot dot. Again, for n times, it would have an eigenvalue n. Okay. This justifies the name ladder operator. So these a plus a minuses are called ladder operators. Why is that? Because you see, as you apply this is like a rung, right? This is the first rung of your ladder. This is the second rung of your ladder. So as you apply a plus again, and again and again, you go up this ladder. You go up this ladder by applying these a pluses, sorry. Likewise, just the opposite happens. You can also go down the ladder if you apply these a minuses, right? So that is this side of the story, going down the ladder. You can start from a particular value of E and you can climb down the ladder step by step. So that's why these are called ladder operators. Okay, great. So the only thing that remains is to now use this knowledge and try actually solve for the eigenfunction. So you see, there was a reason we chose the potential. Now let's go back to the potential, right? This potential was chosen of this kind, the simple harmonic oscillator. So you know how to plot this, right? For example, it looks a bit like this. This is a rough diagram. So this is a parabola. You know that this equation y is equal to alpha x square is a parabola, right? If alpha is positive, then it it escapes to infinity in this manner, and if alpha is negative, you get the opposite. You get something like this. Is, say, minus alpha x square with alpha positive, which is the same thing as saying that, you know, yeah, this is escapes to minus infinity. So in our problem, the ball is sitting, or the particle is sitting somewhere here. In the problem we solved in the last couple of classes, the potential was in this kind, right? The ball was sitting somewhere here. Now the problem we are trying to solve is this problem. The potential looks like this instead of this. This was the last couple of classes. So this actually, when you have a potential energy of this kind, you know, your kinetic energy is half m, say from classical mechanics, you know that it's half mv square, right? And with m greater than 0, the mass of the particle is certainly greater than 0. This is a positive definite quantity, right? So your potential is also positive definite, as you see from here, because of course your spring constant k here, k spring constant, is a positive quantity, right? So the potential is of this kind, which means it's a positive definite quantity. So now let's look at the energy. So what happens to your energy? Your energy, total energy, is T plus V, kinetic energy plus potential energy. And you see individually, both of them are positive definite, right? I should probably put here. Which means that this is actually a positive definite quantity. And this you always demand in physics. You demand your energy is bounded from below. Okay, this is very central in physics, because if you didn't otherwise demand the energy is bounded from below, for example, if you had your potential of this kind, which is this kind of a potential, you see, imagine you have a ball here. Any perturbation that you give, it makes it unstable, right? It just simply rolls off. It rolls off. So this is called an unstable system, and we generally don't deal with such systems, at least not at this level for sure. On the other hand, if you have a potential like this, for example, and you have a ball here, the ball oscillates in this manner, right? It goes up and it goes here and then comes back and goes here and comes back. So this is a stable system. Eventually, if this is dissipative, in the sense that if there is friction, the ball slowly settles down to this central point. So this is a stable system. So here you demand that your energy is actually bounded from below. Here you'll have your energy not bounded, because your potential energy is escaping to infinity, minus infinity, right? So this guy is escaping to minus infinity. So this inequality will always be violated in this unstable system. This inequality will always be violated. Okay, so upshot is that your energy in stable systems is bounded from below, right? Okay, but immediately let's go back and check what we had done. We have found out seemingly the harmonic oscillator has these rungs of ladders, right? Say this is E, this is E plus H cross, E plus H cross, sorry, 2H cross omega, da da da. This goes up. And seemingly this also goes down to minus infinity. But this is precisely what I said cannot happen for a harmonic oscillator, or for any stable system for that matter. Which means there must exist, this is the crucial point, there must exist a psi naught, such that I cannot reduce the energy any further. Sorry, I have a bad throat. That's why I couldn't make a video in the last week. Okay, which means, what does it mean? That this is 0. This is crucial. So let me say it again. We have understood that the energy needs to be bounded from below. This 0 value is not important. What is important is some value. The energy needs to be more than something, some constant. It can be minus 30, minus 20, 10, 1000, minus 1000, whatever, doesn't matter. But it has to be greater than equal to that. That's the whole point. That's what it means to be, that's what it means to say that it's bounded from below. But in this ladder, apparently it seemed that I can really play this game and keep going forever, right? But that has to stop somewhere. That is precisely the hallmark of a stable system. Which means there must exist some psi naught, some eigenfunction psi naught, such that if you wanted to play this game again, or in other words, if you wanted to act A minus again, you would get simply 0. This is the same condition as this condition. Of course, you can act A plus to it. A plus psi naught is fine. A plus square psi naught is fine. And so on and so forth. That's not a problem. A minus has to be annihilated by A minus, because A minus reduces the energy. Okay. If you are convinced, think about this, because this is crucial. Okay. There has to be some mode psi naught whose A minus which is annihilated by A minus. A minus acting on psi naught gives you 0, because that's the ground state. If it didn't happen, then there would be a roll off. Your energy would have kept going on further and further below, and that cannot happen in a stable system. Okay, great. So we are done. Then I know that there must exist a mode psi naught, let's call it psi naught, such that this is 0. Well, I know then it's easy, because I know what A minus is. So A minus is 1 by root 2m times this operator, H cross by I ddx minus I m omega x psi naught is equal to 0, because this was A minus. And this is a first order differential equation, so you can immediately solve for it by pen and paper, or if you're using some tool like Mathematica, you can immediately solve. And let me, since it's been a bit longer than the lecture is getting a bit longer than what I expected, I claim that the solution of this equation for psi naught, it's a first order differential equation, is some constant. So if it's an nth order differential equation, it would have n constants. It's a first order differential equation. It has one constant. And this we have seen in previous classes, that there would be always a constant of integration, which you need to fix from probability interpretation of wave function, or in other words from its norm. And I claim that if you solve this equation, here, well, of course, this 1 by root 2m doesn't make sense, right? Because it's it's 0 on the right hand side. You can get rid of it. So essentially, you are solving this equation, and the solution is this. Okay, this is the ground. This is called the ground state wave function. Right here. Okay, so I know psi 0. I also know the other eigenfunctions. Right? So I'm done. What are the other eigenfunctions? Well, the other eigenfunctions are all this psi 0x, right? These are the other eigenfunctions. Say psi nx is proportional to, because I'm using proportional because there would be respective normalizations, right? Like you had a normalization here. Each of these would have their own normalization. That's why I wrote a proportional here. And you know what this you know what this a plus is, right? So do you recall what this a plus was? Well, this a plus was 1 by root 2m h cross by I ddx plus, here that was a plus, I m omega x, this whole thing acting n times on psi 0x, where psi 0x is given by this function. This is your complete wave function. This is your eigenspectrum. So, and your psi 0 x, I need to figure out the eigenvalue of psi 0x, right? Because in the Schrodinger equation, you see, you need to figure out two things. Something that I wrote here a couple of pages back. Ooh, I already wrote quite a few things. So this is what we have already just now figured out. You need to now figure out this guy. Well, that's easy to figure out, right? Because it's just the solution of the Schrodinger equation with that psi 0. So let's do it. So with that psi 0, let's try and figure out what your an is, what your E0 is, and if you take the psi 0 and you act the Hamiltonian on it, let me write it properly. If you act this size on it, which is a plus a minus plus half h square psi 0 is equal to, let's call it E0, the same 0 here, psi 0. But you already know that a minus psi 0 is 0. A minus acting on psi 0 is 0. So clearly, which implies A0 is half h cross y. Therefore, again, so if I know, now I'm done. So say psi 1, which was proportional, will have an eigenvalue. Do you remember, do you have any idea what the eigenvalue would be? Think, we have already done this. So this is what we did here. So if your psi, say, had eigenvalue E, your A plus would have an eigenvalue, A plus I would have an eigenvalue, whose eigenvalue would be added by H cross omega, and so on and so forth, right? So that's exactly what we have here. So your psi 0 has eigenvalue this, right, from this equation. which means your psi1 will have eigenvalue E0 plus H cross, which is 3 by 2 H cross. So your psi2, which is proportional to A2 square psi0, would have eigenvalue 3 by 2 H cross plus H cross again is equal to 5 by 2 H cross, and so on and so forth, right? So let's write the full spectrum. Your psi0 is A, e to the power minus mh cross, e to the power minus m omega, sorry, m omega by 2h x square, and it has eigenspec E. This is psi. This is eigenvalue half H cross. Psi1 has psi0 is proportional. I shouldn't again write equal to, it's proportional. It would have eigenvalue 1 plus half cross, so on and so forth. So psi n generally is a plus n. Psi0, it would have eigenvalue so countably infinite eigenspectrum. Because these are labeled by n equal to 1, 2, 3, these n's. These are natural numbers, right? So this is your eigenspectrum for the simple harmonic oscillator given by this this line. So yes, we have solved the simple harmonic oscillator. We have figured out both the wave functions here and the eigenvalues, right? So that solves the eigenspectrum problem. So in the next class, we'll do the same. We'll figure out these eigenspectrums that we have here via the algebraic method, which is also quite nice, quite interesting. It just brings in new features that I want to discuss in the next lecture. So that's it for today. And if this was helpful, try and go through the past lectures, try and figure out what we did in the last couple of lectures, and like and subscribe and share these videos with your friends. So see you next time. Bye.